Welcome back to AI Peer Review. Today, we're really getting into something critical in deep learning, especially for areas where you just can't afford to be wrong, like, say, medical diagnosis.
Exactly. It's not just about getting the right answer, it's about trust. And a huge piece of that trust puzzle is understanding how confident an AI model is in its own prediction.
Right. Is it a slam dunk or is it, guessing? We're looking at a really interesting paper today that tackles this head on.
That's the one. Because look, deep neural networks, amazing predictors, no doubt. But if you're using one to help spot something in a scam, just getting the yes or no isn't enough.
You need the how sure are you part.
Precisely. Is the model absolutely certain, or is this a borderline case where, frankly, a human expert needs to take a second, maybe even a third look? That uncertainty score, it's vital.
Absolutely. And there's a technique lots of people use for this, right? Monte Carlo dropout or MC dropout.
Yeah, it's pretty common. The idea is, well, quite neat, actually. You take your already trained network, but when you go to make a prediction on new data, that's the inference step, you switch dropout back on.
Which is usually turned off during inference, right?
Usually, yes. But here, you turn it on, and you run the same input through the network multiple times. Each time, dropout randomly switches off different neurons.
So you get slightly different results each run.
Exactly. And the spread or variation in those results gives you a statistical estimate of the model's uncertainty. If the outputs are all over the place, the model's probably not very sure. If they're tightly clustered, it's more confident.
Okay, that makes sense. It's practical. You don't have to retrain everything.
Right. But, and this is the big but the paper focuses on, standard MC dropout typically uses fixed dropout rates, like one rate decided during training maybe.
One rate for everything.
Pretty much. Same rate applied to every layer in the network and for every single piece of data you feed it during inference.
That feels blunt, doesn't it? I mean, different inputs must be harder or easier, and different layers are doing totally different jobs. Some are finding edges, some are putting concepts together.
You've hit the nail on the head. It is blunt. A single static rate. It just can't be optimal across the board.
So what happens if the rate's too high?
Well, if it's too high for a specific layer, or maybe for an input that's actually quite clear, you might just be injecting way too much noise. You could actually mess up the prediction itself by randomly dropping too much useful information.
Okay, so you heard accuracy. What if it's too low?
Then you have the opposite problem. If the rate's too low, especially for a really ambiguous input or a layer that's critical for subtle details, you might not be creating enough variation. You don't properly explore how sensitive the model is to small changes.
So you don't capture the true uncertainty. It might look more confident than it really should be.
Exactly. You get a poor estimate of the actual ambiguity. And many existing methods try to find a good fixed rate during training. But then you deploy the model, it sees new data, maybe slightly different data.
That fixed rate has no clue how to adapt. It's stuck.
Precisely. The paper uses Figure 1 to show this really clearly, especially for medical image segmentation. If you look at the uncertainty maps part, the bottom row is the standard approach with a constant rate.
Yeah, I see that. The uncertainty looks speckled. It's just kind of vaguely everywhere.
It's diffuse, right. Now compare that to the top row in that section, which uses the paper's method. Same image, but look how the uncertainty is concentrated.
Whoa, yeah, it's right along the edges. The boundaries between the different tissues in that prostate MRI example, those tricky spots.
Exactly, the spots that are genuinely difficult, even for experienced radiologists, to outline perfectly. The standard method gives you noise. This method seems to highlight where the model is actually struggling.
And there's that red line showing the actual segmentation error. The top row's uncertainty lines up way better with that error than the bottom one. That seems much more useful clinically.
Absolutely. A doctor seeing that knows immediately, okay, the AI's unsure here. Let me focus my attention on this boundary. The diffuse map doesn't give you that specific guidance.
Okay, so the problem is clear. Fixed rates equals optimal uncertainty.
Yeah.
So what's the fix? This rate-in method.
Rate-in. It stands for rate-in, information-driven adaptive dropout rates. The name kind of gives it away.
Adaptive, so it changes the rates.
Yes, dynamically, during inference. And here's the kicker. It adjusts the rate not just globally, but per layer and even per input instance.
Wait, per input. So if I feed it an easy, clear image, it uses one set of rates, but for a really messy, ambiguous one, it uses different rates on the fly.
That's exactly the idea. And crucially, it figures this out without needing the ground truth label for that input during inference. You don't need to know the right answer to adapt the uncertainty estimation.
Okay, that's a huge plus for real-world use.
Yeah.
But how? How does it know how much noise to add or remove if it doesn't know the correct output? Magic.
Ha! Not quite magic. Information theory. That's the information-driven part.
Hmm.
Radon fundamentally shifts how we think about dropout. It's not just regularization, it's a tool for controlled noise injection.
Control noise
Mm-hmm.
based on information, like
Yeah.
how much useful stuff is getting through a layer.
Pretty much. It tries to quantify the information loss that occurs when you apply dropout to a layer's activations. It's feature map.
Okay.
It sets a target, basically a budget, like, okay, for this layer, for this input, I'm willing to tolerate this much information loss, let's call it epsilon. Then it adjusts the dropout rate specifically for that layer and input until the measured information loss hits that target epsilon.
So it's constantly checking and adjusting. Figure 2 in the paper seems to show this loop.
Yeah, figure 2 illustrates it nicely. Input hits a layer, dropout is applied with whatever the current rate is. Then radon measures the information integrity, how much signal got scrambled or lost compared to no dropout.
And compares that to the target epsilon.
Right. If the loss is too high, back off the dropout rate a bit. If the loss is too low, meaning not enough variability is being introduced, increase the rate. And this happens layer by layer as the data flows through.
Ah, I see. So for each piece of data, it's finding this unique sweet spot for every layer. Enough dropout noise to gauge uncertainty, but not so much that it corrupts the signal needed for a good prediction. It's a balancing act.
That's the core idea. Algorithm 1 lays out the formal steps, showing how it iterates a few times, up to n max, for each layer to find that right close to the target epsilon.
Okay, let's maybe get slightly more technical for a moment.
Yeah.
How does it actually measure information loss? You mentioned information theory.
It uses a concept called mutual information, or MI. MI basically measures the dependency between two variables, how much information they share. Here, radon estimates the MI between a layer's input activations and its output activations after dropout has been applied.
So dropout breaks some of those dependencies, reducing the shared information.
Exactly. That reduction in MI is the information loss it's tracking.
Calculating MI on these high-dimensional feature maps sounds computationally expensive.
It can be, yeah. The paper acknowledges that. Computing it directly is often intractable, so they use efficient estimation methods. They mention things like adaptive binning estimators to get a good approximation without killing performance.
Got it. So practical estimation techniques. And just to recap the process for single layer and input, start with a rate, apply dropout, estimate MI loss compared to epsilon, adjust rate up or down, repeat maybe a few times.
Yes, that's the iterative refinement loop. It runs for each layer, for each input instance. Decrease the rate if the loss is too high, too much info lost. Increase it if the loss is too low, not enough variability introduced for the target epsilon, until it settles near the target or hits the max iteration limit.
That dynamic adjustment per input now makes perfect sense. It's tailoring the process right then and there. Okay, theory sounds good. But does it actually work better in practice? What do the experiments show?
They started with a synthetic regression task. Nice controlled environment, you know. You can precisely vary things like noise levels and the amount of training data.
And how do you measure how good the uncertainty is there?
A key metric is the ratio of the uncertainty interval width to its coverage. Basically, you want tight intervals, narrow estimates that still manage to capture the true value most of the time. Lower ratio is better, more precision for the same reliability.
Makes sense. And figures 3A and 8, they show radon.
Yes, those figures compare radon to baselines, like using a constant rate or a pre-scheduled rate. Across different noise levels added to the synthetic data, radon consistently gets a lower, better interval width to coverage ratio.
So sharper, more efficient uncertainty estimates, even when the data gets noisy.
Exactly. And figures 3B and them show another angle. Radon maintains its advantage even when you have less training data. That's huge because limited data is a constant challenge in real-world AI, especially medicine.
Good point. And figure 10, what's that showing?
That shows the convergence. Basically, the radon optimization process finds a stable dropout rate reliably, regardless of where it started from initially. So it's robust in that sense.
Okay, synthetic tests look promising. How about the real-world medical stuff?
Right. They looked at segmentation and classification. We talked about segmentation earlier with figure 1, how radon gave those focused uncertainty maps along boundaries.
Yeah, highlighting the tricky bits, not just random noise.
And table 2 backs that up with numbers. They measured things like expected calibration error, or ECE lower is better, means your predicted confidence matches reality better. And boundary uncertainty coverage, BUC higher is better means uncertainty is concentrated at the edges where you want it.
And Radon did better on those.
Yes, especially in challenging anatomical zones like the transitional zone in prostate segmentation, which is notoriously ambiguous. Radon had lower ECE and higher BUC there compared to benchmarks.
So the uncertainty isn't just random, it's actually pinpointing known difficult areas. That's impressive.
It really demonstrates the value of being adaptive. Oh, and Figure 4 had an interesting side note about the UNet architecture they used.
What was that?
The decoder layers, the ones building the segmentation map back up, were way more sensitive to information loss from dropout than the encoder layers that just extract features.
Huh. That makes sense, intuitively. Messing with the final assembly stages is probably more damaging.
Right. And it really justifies Radon's layer-specific approach. A single fixed rate would be punishing those sensitive decoder layers potentially, or not challenging the encoder enough.
Good point. Okay, what about classification tasks?
They use the MetaNIST datasets. These are standard benchmarks, collections of medical images like pathology slides, blood cells, tissue samples. Table 1 and Figure 11 show the results.
And the story there.
Pretty consistent. Radon generally maintained high classification accuracy while significantly improving uncertainty calibration. They measured this with AU-arc area under the accuracy rejection curve.
AUR. What does that capture again?
It essentially measures how well the model's confidence predicts its own errors. A high AU-arc means you can effectively improve overall performance by having the system flag or reject the predictions it's least confident about. You trust its self-assessment more.
So it's better at knowing when it doesn't know.
Exactly. And Radon really shown here, especially at higher target dropout rates where the baseline methods started to fall apart in terms of calibration and even accuracy. Radon held up much better. They also noted different MetaMinus datasets had different sensitivities, again highlighting why adaptation is key.
Okay, so it handles standard benchmarks well, but real life is messy. Corrupted images, artifacts. What about out of distribution or O data?
They tested that too using MetaMinus C. The C's is for corruptions. They added various realistic image problems like blur, noise, contrast issues. Table 3 and Table 5 in the appendix cover this.
And Radon was more robust.
Significantly. It maintained higher accuracy and better AUR's calibration compared to the baselines across many of these corruption types. It suggests Radon is more stable when faced with the kind of imperfect data you'd actually see in practice.
This sounds really powerful for making AI more trustworthy in critical areas.
Yeah.
But there's always a but. What's the catch? Computation time.
Yeah, that's the main trade-off. This dynamic, per instance, per layer optimization, it takes time. Radon adds computational overhead during inference compared to just doing a single pass with fixed dropout.
How much overhead are we talking?
They give the theoretical complexity and some actual timings in tables 6 and 7. For, say, a 2D image on a reasonably sized model, maybe it adds less than a second. But for large 3D medical volumes, it could be several seconds, maybe more.
Okay, so definitely not free. That's something users would need to weigh against the benefits for their specific application, especially if latency is critical.
Absolutely. The paper does suggest you might be able to do some pre-computation or offline optimization for a known data distribution to find good starting rates, potentially speeding up the online inference part. But yeah, it's an extra cost.
Are there other limitations they mentioned?
A few. They acknowledge that mutual information, while powerful, might not capture every single aspect of information relevant to vision tasks. They even played with SM, another metric, in the appendix.
And that target information loss, epsilon. That sounds like a parameter you'd need to tune carefully.
It is. It's a hyperparameter. You'd need to choose it based on the task and how you want the uncertainty to behave, likely through empirical testing. Different epsilons will give different results.
And finally, dropout itself has limits, right?
Right. Radon optimizes how dropout is applied, but dropout fundamentally works by zeroing out individual neurons. It might not be the best way to capture uncertainty caused by, say, global image noise or broader issues that affect the whole input space.
So it makes MC dropout much smarter and more adaptive, but it's still working within the framework and limitations of dropout as the noise source.
Precisely. It's a very clever enhancement to that framework, not a replacement for entirely different uncertainty approaches.
Okay, let's pull this all together. What's the big takeaway from digging into Radon?
I'd say it's a really practical, unsupervised way to make uncertainty estimation better during inference. It uses information theory to intelligently adapt dropout rates for each specific input and each layer.
And the payoff seems clear from the experiments. Better calibrated uncertainty, Sharper uncertainty maps that actually highlight problem areas in segmentation, maintained accuracy, and better robustness when things get noisy or weird.
Yeah, all really desirable properties, especially when you're thinking about deploying AI where mistakes can have serious consequences, like in medicine. Reliable uncertainty is key for trust.
It definitely feels like a step towards making uncertainty estimates less of a black art and more of an actionable signal, using a familiar tool like Dropout, but in a much more refined way.
It's elegant, really. Using information theory to guide the process feels right.
So, thinking ahead, given how vital trust and reliability are becoming for AI, especially in sensitive fields, how might these kinds of dynamic data-driven methods like RAID-in change how we approach deploying models? And maybe what other kinds of noise or fundamental uncertainties are still out there that we need to get better at capturing? Definitely something to ponder.